Okay, hello everyone. I'm glad to be here today. Thanks for the invitation. So I'm Pierre-Alexandre Léziart, 1 week old postdoc in the Joint Robotics Laboratory here in Tsukuba. And until last month, I was in the Gepetto team at La CNRS in France. And so today we will talk about whether we should learn or optimize artificial locomotion, a talk which has been prepared with the help of Nicolas Mansart, a senior researcher in the Gepetto team. And since it's the last presentation of the last day, I try to keep things high level with a lot of videos to keep that lively. So first, as you can see, compared to a decade ago, we now have access to a wide variety of leg robots, and even more since these snapshots were made, as you have probably seen in the exhibition hall. And so we have this complex leg system, and we need solvers to control them, and controllers. And so for that, the state of the art of a few years ago, which kind of still is the state of the art since you can already get pretty good results with that, is just to use good old control heuristics. And for that, you have, for instance, the stack of tasks, which consists of stacking a task of increasing importance. So first like the support foot and then the center of mass. And so the solver will first try to respect the support foot task, and then based on the remaining degrees of freedom or the kernel of this task, it will solve the next task and again and so on, with then a small regularization just to control the remaining degrees of freedom after the whole stack. And so with that, as you can see, we can already do some 3D locomotion with a quadruped robot, with the MPC and some heuristics to make the footstep planning. And so this was, Solo 12, this is a Solo 12 quadruped, so it is blind, so we were providing information about the terrain with the motion capture system. So we have this good old control heuristics, but now we are trying to go more and more to our more whole body control decisions. So we are, instead of using heuristic, we are more expressing high-level function objectives, and then we let solvers exploit the model of the system capabilities to generate the whole body motion intelligence. And so what do we need from a solver that is able to do that? First, let's focus on just a brief recap on model predictive control. I will go quickly since I guess most of you already know that. And then we will talk a bit about the learning part. For predictive control, that is important because it will have a link with the learning. So from the predictive control, we want to decide a future robot trajectory of our prediction horizon. So from the current state of the bike to the end of the road, which will be the end of our prediction horizon, while optimizing an objective function. Let's say just keeping in the middle, staying in the middle of the road. And for that, we want to impose constraints. The known initial state, that is the current state of the system, we cannot directly change it. It's not a variable. We have an evolution model and some other constraints, like on the actuation or, I don't know, on joint limits, for instance. If we express that in a mathematical way, so we have, again, a minimization problem over a prediction horizon. We want to minimize a cost function with some constraints, the initial state, and a model of the dynamics and other constraints, if you want. And so we are doing this prediction, this whole dotted green line over the whole prediction horizon, even if we just want to use just the time step, just the immediate control decisions that we will directly send to the robot. Yet it is still useful to have this prediction because it kind of gives us guarantee about what is going to happen based on the model of the system, even in situations that are unforeseen and that have kind of never happened, which is something that we don't really have with the learning aspect. And so what do we need from an efficient solver to do this kind of predictive control? With a good, if you want a good solver, you want a stable prediction that is to have a multiple shooting approach, not only doing an integration over a single segment on the whole prediction horizon, and instead have several small segments, as Patrick Voensing talked a bit about during his presentation. You want sparsity, that is that this kind of optimal control problem, like for leg robots, usually they have this kind of structure. So at 2 levels, you have temporal structure, because like which generate a block sparsity. So like each time step of the prediction horizon will be like several blocks and then a lot of zeros. So you want your solver to avoid like losing time processing all these zeros. And also at the kinematic level on the left here, you have some sparsity just because, let's say, the action on one foot will not directly impact the movement of the hand, and so you have some, again, some zeros that ideally your solver should be able to use. And in the team, for us, we are using a Pinocchio, which development is led by Justin Carpentier. And that exploits the sparsity aspect. And so for sparsity, you have also differential dynamic programming, so which does this backward pass through the node of the prediction horizon, and then a forward pass to get the forward dynamics based on the decision on the actions that have been generated. And finally, you want a solver that is able to get to handle strict constraints, like a strict, I don't know, jump limit or strict motor strength that you don't want to overshoot. And for that, you have, for instance, the augmented Lagrangian approach, which convert this constraint problem into an unconstrained one by converting the constraint into penalization. So one penalization term per constraint plus an augmentation term which comes from the augmented Lagrangian. And for that, the Crocodile solver whose development is led by Carlos Mastali, it was a bit presented this morning. As like these videos also we have already seen it, is able to do all of that, and so that's what we use mainly in the team, able to control our leg robots in real time, so even with thousands of variables in the classical like quadruped or humanoid problems. But we are still trying to get with our collaborators and that we work with other more advanced numerical solvers. So with the sequential quadratic programming approach, which you have seen on the poster and which was one of the finalist poster, which is using a sequential quadratic programming approach, so which solve a series of QP problems. I hope I'm not wrong. So a series of QP problems, one QP per constraint, and then inside this QP, you can solve them, for instance, with USQP, which is an augmented Lagrangian solver, and so these constraints are converted into an unconstrained problem, linearized, and so you can use a Riccati loop inside to solve and to respect the constraint in an efficient way. For that, it is part of it is from the work from the New York University team and part of Crocodile also. And another approach is this time more from the Willow team of INRIA, which is not to have a SQP, so with QP inside and this QP are augmented Lagrangian. It's instead to have a single wall augmented Lagrangian approach, which will again convert this constraint into an unconstrained approach with this Lagrangian term. And this time the contribution is in terms of numerical stabilities that are that in general when you approach the constraint, these penalties can go up to infinity and create some kind of bad numerical behavior. And so thanks to the proximal approach, you can avoid this explosion of the penalty term, or at least the problem stays stable. And again, that is implemented as part of the Alligator, which is kind of based on Crocodile. So with this solver in general works pretty well when all this solver works pretty well when you are kind of close to the optimal solution, but sometimes they can struggle when you are too far from, they can fall into a minimum, local minimum, or they can take too many iterations to converge properly for you to be to have real-time performances. And for that, in the team, we had this idea of having a memory of motion that is to offline, so before you deploy that on the robot, offline to generate a bank of optimal trajectories that you spend a lot of time to to compute, to be sure that you have the proper optimal solution. And then at runtime, you can pick in this bank of optimal trajectories to warm start your solver close to the optimal solution. Let's say by taking the trajectory whose initial state is the closest from the current state of the robot. And so that is one way to solve or to avoid this kind of bad numerical behavior due to the warm start of the solver. And so when everything goes well, you can have this kind of behavior. So this one is a solver from the Willow team. And so this can be applied for leg robots, but also for robotic arms. So just reaching the red targets while having some hard constraints, which are the collision in this case with the pink cylinders. We have that in simulation, so in real time, but you can also have that, so of course, deployed on real robots. I'll just launch the videos. So first on the left, just showing the capabilities of these kind of solvers to replan in real time over the whole prediction horizon, avoiding collision or handling disturbances from a human operator. Or on the right, an interesting approach which so again from the New York University, an interesting approach in terms of contact handling, so a task with force feedback in the controller using a force sensor at the tip of the robotic arm, so in the middle of the screen. And usually it's not really possible to do this kind of force feedback because when you have a rigid contact model, when you are in contact and you choose your joint torques due to the contact constraint, it directly enforces contact forces. And so it's not a decision variable, only the joint torque are decision variables. And so to achieve this decoupling between the joint torques and the contact forces, you can consider the contact as an elastic contact. And so that way, the contact forces are a function not of the joint torque, but of the deformation of the contact surface. And so you can have them as optimization variable in your control problem. And again, you can do that in real time without issue. Other kind of things we try to do, so we had these contact forces, but also with our colleague in Prague, with Médéric Formy, which was in the team before, is to add visual feedback as part of the control loop by adding this position, this desired position and detected position of the object as part of the state. Or on the right with Arthur Hafmeyer, to have collision avoidance, this time by including the sign distance with the half sphere in the problem. And so you have, again, real-time collision avoidance with these constraints. So you can do robotic arms, but of course you can do leg robots, one of the main focus of the Gepetto team. So it does not launch. Okay, we just. Okay, so you can have this locomotion in real time with a whole body torque control on a human robot, so with the whole footstep selection that are part of the control loop, and with disturbance, it can handle disturbances if you push it a bit on the side, and so we have that in real time on the Talos robot. And you have also on quadruped with whole body controllers that run in real time, able to handle disturbances, follow a body velocity reference with an adaptive footstep planning. Okay, and something that you have already seen this morning, so a whole pipeline on the animal robot by our colleague in Edinburgh. Again, with the whole body control for animal robots, with the whole pipeline, so footstep detection of the terrain, segmentation of the surfaces, footstep selection, and model predictive control, all in the loop in real time. And just something also, just quickly, because I have the time. So again, you can also apply that for exoskeleton with our colleague in Wondercraft. Now, to make the transition to learning, because that was one of the points of this presentation, basically both are, if you are trying to solve this kind of problem, so starting on the bottom left and like starting on the bottom right and like going to the target position on the bottom left, if you are seeking this whole trajectory from the current location to the target position, you are more in the family of predictive control, which has some interesting characteristics, like you will know what is going to happen in the future if you follow the current action and based on your model. And instead, if you are seeking this whole vector field, so you are seeking a policy in the whole workspace, you are instead in the family of learning. Again, with the advantages that you have just you have that on the once you have it on the whole workspace without recomputation of a whole prediction problem. And since in the Gepetto team, historically, we were more model predictive control team back from our work on RCP2 back in 2006. With the rise of reinforcement learning, we wanted a bit to explore a bit what was going on with that, to have a bit of a grasp of these two important aspects that are now leading to really good results on both sides. And so that's why on our Solo 12 robot, we have first just deployed a simple reinforcement learning policy, so just outputting the classic joint target position with respect to a default configuration, and after learning in Isaac Gym, so with thousands of robots in parallel, which is a nice thing that we have since a few years ago, due to so that we can run thousands of robots in parallel and just get this kind of policies in like 1 or 2 hours. And then, yeah, you have a high cost of training, and then once it's done, it's really fast in terms of inference time compared to the model predictive control, where you have to do the whole solving again and again, even if you go back to a previously visited state. But if you want to get nice behavior, a bit like this one, but if you want to go even further with things like starting to climb on obstacles and stuff like that, it can be, the learning approach can become quickly a bit of a pain to deal with, because you will start to stack a lot of different rewards in your reward function. You will also have, if you want to enforce constraints, you can do that with like penalties that are going to be enabled when you cross the constraints with a really high weight. And so you can like quickly end up with like maybe 10 or 15 rewards that you have to properly tune. It takes a lot of time to do that, especially when it takes like, I don't know, like 4 hours to get results. And so in recent years, there has been a push toward constraint Markov decision process for constraint reinforcement learning. That is to instead to having these constraints just as reward mixed with the other task reward and so on, to really have a formulation that takes the constraint as part of the learning architecture, kind of. And so you have this standard expectancy of the discounted rewards, but you have also an expectancy of the discounted cost or constraint return that you want to be under a given value, so which can be 0 if you want no violation of the constraint at all, but you can give it some slack if you want to allow some punctual violations. And so I have recapped a few methods that are presented in the paper in the bottom left. So a few methods that have appeared in the recent years that deals with constraint reinforcement learning. So you have a penalized PPO, which formulate the constraint with an additional term in the loss function, in the traditional PPO loss function. So you have the PPO loss minus some loss that come from the violation of the constraint. You have PPO Lagrangian, so a bit like the augmented Lagrangian approach. It's turned the constraint problem into an unconstrained one by adding a dual term in the loss function, and so the solver will alternate between the primal and the dual to do this gradient during the gradient optimization. Then you have the IPO approach, which is inspired from the interior point approach for the classic model predictive approach, which is a bit in a way similar to P3O, but instead of just having like minus the constraint violation, you have minus the constraint violation inside a logarithmic term which does that when the system is getting close to a constraint, it creates an infinite penalty, and so a really strong gradient that will push the network toward a non-violation of the constraints. Then you have CRPO, which just most of the time just try to optimize the rewards, and when there is a constraint violation, it stops looking at the reward and it only tries to solve this constraint violation, and once it goes back to a normal behavior, it keeps again to just solving for the rewards. And finally, you have FOCOPs, which solve policy, which does this optimization in a policy space and then project it back to parameter space, which is kind of equivalent to having an unconstrained learning architecture. And for so as you have seen, all what I've just described kind of brings additional complexity and kind of bring like little tricks, and you have to, if you want to implement that, you have to do it well, or otherwise it does not work at all. And so what we wanted in the team when we were trying to go toward constraint reinforcement learning is to find a really simple approach, like the simplest we could find, just so that we would reduce the computational burden and make that more available to the community by avoiding a bit of implementation complexity. And for that, we took the approach of the chance constraints, that is to, instead of having an expectancy of the discounted return of the constraint, we are not looking at the expectancy, but rather at the probability of constraint violation, so that you can see in the middle on the left. And so then, based on that, you can reformulate it just but with with a term that is going to affect the termination chance. So, like when you have no constraint violation, the termination chance is just at 1, for instance. And the more constraints are violated, the more termination chance there is. And so maybe at each time step, the environment will have a 10% chance to be killed. And if it violates even more, a 20% chance, and so on, it keeps increasing. And we also apply this delta term to the reward, so it both affects the termination chance and the total rewards. And that way, it kind of guide the learning toward a behavior that does not violate the constraints, to avoid early termination and to maximize the reward. And as you have seen, we can already get pretty nice results in 3D environment with really a simple implementation that is like a few lines added on top of PPO, like maybe like a 10, yeah, I don't know exactly, but maybe 10 lines, let's say, on top of PPO, depending on how you write it. And in terms of observation vector, we are just giving the proprioceptive information, not even like a teacher-student setting, just pure proprioceptive information and the past action. If I am now to make a bit of a recap of what we have seen in terms of strengths and drawbacks of both, which is something that you have seen also a bit the same thing this morning, which is that on the left you have more the model predictive approach, which is very nice in terms of that you are going to have a trajectory of our prediction horizon, which give you kind of guarantees about what is going to happen in the future, but with drawbacks that are that there is no memory, so you keep there is a high computational cost. You keep solving kind of for the same thing. The risk of falling into a local minima if you don't have a proper conditioning of the problem. Difficulty with the discontinuous dynamics that are mostly a bit like when you have an uncertainty about the contact or discontinuous dynamics, it's a bit hard to formulate that properly into a model predictive problem. And again, for the multimodal sensing, it's a bit of a side thing compared to what I've shown, but like how do you like put a sound sample or a depth image directly into a model predictive problem? It's not that trivial. You have to do some adaptation compared to the learning approach where you can put whatever you want as input. You can provide it with what you want. It has once the cost of training is done offline, once you have good globalization capabilities, but the drawback of the others, they are a bit complementary, so not really strict constraint satisfaction. You have this constraint reinforcement learning approach, but it's never strict constraints. You can have some violation at runtime. And so the answer to the initial question, should we learn or optimize, that you have probably already seen with the presentation of this morning, is a bit cheesy, but it's we should both learn and optimize the artificial movement for the artificial movement of robots, because they have both really interesting points that I've just said before, like in terms of convergence, of exploiting the dynamical knowledge that we have about the system. That is really nice, but on the other side, we could really use this capacity of the policy learning to kind of grasp an optimal policy in the world workspace, and maybe so link the two. That is something that is already done, so that we have seen this morning, and also just this week, maybe I have seen, I don't know, maybe at least 5 papers that are kind of linking and using both model predictive control and policy learning. In both directions, so you have like these MPC to reinforcement learning, like generating reference trajectory with an MPC and then giving that to the neural network, like with imitation learning, and then just fine-tuning the behaviors that you get. And that is a way to avoid all the pain of having the robot initially a bit moving randomly, which greatly improved so by providing these reference trajectories, you can have an increase in the sample efficiency. Or the other way, which is what we have seen this morning with, if I remember well the name, with Cacto, or with other methods, that is to have the other direction, learning toward MPC, so by like either learning a model of the system, because like in MPC we have to use template models. With a neural network, you can kind of grasp things on the real system that are too hard for us to model. Or you can also like provide reference trajectories for your MPC based on a bank like we had with a memory of motion, this kind of stuff. So I think in the coming years we are going to see more and more approaches that are going to combine the two a bit just to take the best of both worlds, because just brute force policy learning is a bit sad, knowing all the strengths that we have in theory for the model predictive control. Thank you.
Thank you very much, Jean-Pierre. No, sorry. Does someone have some question? All right.
So thank you for the presentation. So you show at a certain point that you are using an SQP, OSQP solver with Riccati-based linear solver. Are you using, did you wrote the Riccati linear solver, or are you using a specific library, or?
So for that is so the work by the New York University, so the team from the New York University, so I don't know exactly how it was done, but I guess you can ask, since the authors are in the room. Or I don't see them. No, I don't know exactly how they did that.
Because I'm also using OSQP, but I didn't know about the Riccati linear solver.
But I think it's included directly in the OSQP as part of OSQP.
Okay,
So great. It's internal. It's like a loop inside each QP of the of each internal augmented Lagrangian problem.
Okay.
So it's internal.
Thank you.
All right.
Hi, thank you for your presentation. I saw there's one page to introduce the memory. So what's the difference? Like, here is the something like the offline, or you collect some data? I'm not sure what kind of memory you use or how to use.
So for this one, it was mainly offline optimization. So you can use this really strong nonlinear solver that can take maybe 1 minute to get a good trajectory. But so you gather a lot of trajectory, like you sample initial state on the whole possible working space for all kinds of, let's say, target positions that you want. You build this whole bank, you solve 1,000 of trajectories, and then you store them in this like memory in which you will sample later when you are at runtime. So it's the initial way we did it, yeah, was just so to solve trajectory and store them, and we tried a bit to have that link to a neural network that will kind of learn on this bank of trajectory to directly like output an optimal trajectory by learning on all the workspace.
So you don't run the memory section online, right?
The memory is just that we keep in memory all the optimal trajectories that we have computed offline, and that at runtime we pick one trajectory in all this bank of data, and so that is the aspect of that is why we say memory, kind of just picking a memory of what we have done offline to warm start the solver at runtime.
Okay, thank you.